Light is reaching your eyes right now. Some of it just crossed a pane of glass, part of every beam reflected while the rest passed through. You were told each particle of light simply followed the odds, and that a smarter theory could say which way each one went. It cannot. Not because our instruments are crude, because the answer was never written down anywhere. Flip a coin and the outcome hides in the physics of your thumb. Split a beam of light and nothing hides at all. Physicists went digging for the machinery beneath that chance. In 1926, Max Born wrote a single formula for the odds. In 1957, Andrew Gleason proved something unsettling about it. And John Bell spent years hunting for the hidden answer. This is the Born rule, the formula that turns quantum mathematics into a number you can measure, tested to better than a part in a trillion, and the one they proved has no deeper flaw beneath it. The chance is not covering for missing knowledge, the chance may be the bedrock. So this is where it starts. Let me show you the machine at the center of all of this, because it is almost insultingly simple, and its simplicity is the whole problem. Picture a single particle of light traveling toward a half-silvered mirror, the kind of coated glass that reflects half the light striking it and lets the other half pass. Send a bright beam at it and the accounting is boring. Half the energy bounces, half goes through. But send one photon and one photon cannot split. It arrives whole at one of two detectors, bounce or pass. One click on one side. Do it again and it might go the other way. Do it 10,000 times and almost exactly half go each way. So where does each individual photon go and why? That is the question this whole story is built to answer, and the honest first answer is the strangest thing in physics. The mathematics that describes the photon does not contain the answer. It contains a wave, an abstract object called the wavefunction, written with the Greek letter psi that spreads down both paths at once. The wavefunction is not the photon. It is a bookkeeping device that carries, for every possible outcome, a number called a probability amplitude. And here is the rule that connects that abstract number to the click you actually hear. Take the amplitude for an outcome, square its magnitude. That squared value is the probability of getting that outcome, nothing more. That is the Born rule, and in its cleanest form it reads, the probability of an outcome equals the squared magnitude of the amplitude for that outcome. In symbols, p of x equals the modulus of the bracket x psi squared. Say it plainly. The chance of a result is the overlap between the state you have and the outcome you are asking about, and then you square that overlap. The amplitude can be positive, negative, even a complex number with an imaginary part. Squaring its magnitude throws all of that away and leaves a clean, real number between 0 and 1. That number is the only thing the theory will ever tell you about a single measurement. Not which detector, just the odds.
Why square it? Why not the amplitude itself or its cube? Hold that question because it becomes the hinge of everything, and the answer took 31 years and a mathematician who was not even trying to solve it. For now, notice something about the man who wrote the rule down. In 1926, in a paper on how particles scatter off one another, Max Born proposed that the wave function gives the probability of where a particle lands. And in the first version of that paper, he got it slightly wrong. In the main text, he wrote that the amplitude gives the probability. Then, in a footnote added while the paper was already in proof, he corrected himself. The probability is proportional to the square of the amplitude. The single most important interpretive rule in quantum theory arrived as an afterthought, wedged into a footnote by a man who was not certain of it. What does it mean that the discoverer of the rule that governs every quantum measurement ever made had to correct it in the margins? It means we should be humble about how well anyone understood it, including now. Born won the Nobel Prize for this in 1954, 28 years later, which tells you how long it took the community to absorb what he had done. He described the essence of it in a line worth keeping in mind. The motion of particles follows probability laws, but the probability itself propagates according to strict causal law. Read that twice. The wave evolves smoothly, predictably, deterministically. Only when you look does the randomness appear. The determinism and the chance live in different rooms of the same house. That smooth evolution has its own equation, and it is the other half of the machine. The Schrödinger equation tells you exactly how the wave function changes from one moment to the next. Feed it a state now, and it hands you the state later, with perfect precision, no chance involved. If the Schrödinger equation ran the whole show, the universe would be a clockwork. But the Schrödinger equation never produces a single definite outcome. It produces the spreading wave, both paths lit at once, the photon on both sides of the mirror. The definite click, this detector, not that one, comes only from the Born rule, and the Born rule speaks only in probabilities. Two rules, one deterministic, one probabilistic, bolted together, and no one can fully explain the seam. That seam has a name, the measurement problem. Think of it like this. Imagine an accountant whose ledger balances perfectly all year, every transaction tracked, every column reconciled, except that once a day, at a moment no one can predict, a single entry simply appears, correct and unexplained, with no transaction behind it. The books are exact, and the books are haunted. That is quantum mechanics. The wave function evolves like a perfect ledger, and then measurement writes in an entry the ledger never authorized. Where does the entry come from? Keep that ghost in mind. We will come back to hunt it. Now, why should you believe any of this rather than assuming we are just missing information? This is the reasonable objection, and you should make it out loud, because it is the belief almost everyone starts with. When we call a coin flip random, we do not mean the outcome is uncaused. We mean we are ignorant of the exact force, angle, and spin of the thumb. Give a fast enough computer perfect data about the flip, and it prints heads or tails before the coin lands. The randomness is in us, not in the coin. So the natural assumption is that quantum randomness is the same, that the photon already knows which way it will go, and we simply lack the finer details. A better theory would fill them in, and the chance would vanish.
That assumption is not foolish. It is exactly what Albert Einstein believed, and Louis de Broglie and Erwin Schrödinger himself, three of the people who built the theory. Einstein was convinced quantum mechanics was incomplete, that a deeper and fully predictable layer had to exist beneath it. These are not naive positions. They track a real, respected scientific program. Find the hidden variables, the finer details the wave function leaves out, and restore a world where every outcome has a reason. For 30 years, that program looked wide open. The story of this rule is the story of physicists trying to dig beneath the chance to find those hidden variables and what they hit when they dug. So let us be precise about what the hidden variable dream actually requires, because precision is what eventually kills it. It requires that before you measure, every possible measurement already has a definite answer waiting. Measure the photon's path, the answer is there. Measure its polarization at any angle, that answer is there too. All of them laid down in advance, consistent, just hidden from view. A theory like that is called a dispersion-free state, a state that assigns a sharp, definite value to every observable at once, with no spread, no probability, no ambiguity. If dispersion-free states exist, the chance is ignorance and Einstein was right. If they cannot exist, the chance is something else. That is the fork in the road, and everything ahead is about which way it goes. Here is where the first real number lands, and I want you to feel its size before you see the digits. There is a theory that is tested against experiment more sharply than any other idea humans have ever devised, sharper than Newton's gravity, sharper than any prediction in chemistry or engineering. That theory is quantum electrodynamics, the quantum theory of light and electrons, and its rule for turning math into measurable odds is the Born rule. In 2023, a team led by Gerald Gabriels at Northwestern
measured a property of the electron, its magnetic moment, written g/2, and compared it to theory. The agreement held to about 1 part in a trillion. Written out, the measured value is 1.00115965218059, precise to the 13th decimal. Sit with the contrast because it is the emotional core of this whole subject. The single most accurately confirmed prediction in the history of science rests on a probability rule that its discoverer footnoted, that leading physicists today still call simply postulated, a rule no textbook derives. It is written down as an axiom and then it just works, flawlessly, forever. What does it mean that our most precise contact with reality runs through a formula nobody can explain from anything deeper? That gap is not a footnote to the story, it is the story. The physicist Sean Carroll put it bluntly. The Born rule is one of the most profound and mysterious principles in all of physics, and it is simply postulated. Perhaps, he wrote, we can do better. That word postulated is the whole tension. A postulate is something you assume without proof because you need it to get started. Newton postulated his laws, and later physics explained them from deeper structure. Physicists have spent a century asking whether the Born rule is like that, a temporary assumption hiding a deeper mechanism, or whether it is the deepest thing there is, with nothing underneath. To answer that, you cannot argue. You have to prove something. And the first proof came from a man asking a completely different question.
Before we get to him, we need the other piece of standard machinery, because the Born rule does not act alone. When you measure and get an outcome, the wavefunction does something violent. It jumps. Before the measurement, the photon state was spread across both paths. After the click, it is entirely on the path where you found it. This jump is the projection postulate, written down by John von Neumann in 1932. Upon getting an outcome, the state collapses onto that outcome and is renormalized to keep the total probability at 1. The smooth Schrödinger wave, and then, snap, the collapse. Nobody sees the collapse happen. We infer it from the fact that a second measurement, done immediately, gives the same answer. Is the collapse a real physical event, or just a bookkeeping update to what we know? That question splits the entire field, and we will return to it when we weigh the competing pictures. For now, hold both halves of the orthodox machine. The wave function squared gives the odds, the Born rule, and the wave function jumps onto the result, the projection postulate. Von Neumann built the rigorous mathematical scaffolding for all of it, including density matrices for describing states we only partly know, and the entropy measure that carries his name. He was one of the sharpest minds of the century, and he also proved something that turned out to be wrong in a way that matters enormously later. Keep that seed planted. Even a von Neumann can build a flawless-looking proof on a hidden bad assumption. Now the mathematician who was not trying. Andrew Gleason was an American working on pure mathematics, the structure of measures on Hilbert spaces, an abstract question about how you can consistently assign numbers to the geometric directions in a space. George Mackey had posed it. In 1957, Gleason answered it, and the answer, translated back into physics, was a bombshell. He asked, suppose you want to assign probabilities to quantum measurement outcomes. Impose one reasonable condition, that the probability assigned to an outcome depends only on that outcome itself, not on what other compatible things you happen to measure alongside it. In 3 or more dimensions, how many ways are there to do it consistently? Take a breath before the answer, because it is the payoff of the whole first movement. The number of consistent ways is 1. Exactly 1. The Born rule. Not the Born rule is the simplest or the best, the only one. Gleason proved that in any Hilbert space of dimension 3 or higher, the single condition of consistency forces the probability of an outcome to equal the trace of the density operator times the projector for that outcome, which is exactly the Born rule in its general form. P equals the trace of rho times E. There is no room for a rival. If you want probabilities at all, and you want them to hang together consistently across every measurement, you get amplitude squared or you get nothing.
Let me make the condition Gleason imposed concrete, because everything turns on it. He used an object called a frame function. Picture every possible complete measurement as a set of directions at right angles to one another, an orthonormal basis, a full set of mutually exclusive outcomes. A frame function assigns a number to each direction such that, across any complete set, the numbers add up to the same total, 1, for a probability. That is the only demand. Your probabilities sum correctly on every possible measurement basis, and they do it consistently. In symbols, the sum over any orthonormal basis of the function equals a fixed weight. Gleason proved that any function meeting this demand, in 3 dimensions or more, must have the Born form. The additivity forces the square.
Think about how strange that is with an analogy. Imagine a cartographer told that on every possible map projection of the Earth, the areas of all countries must sum to the same total surface. That sounds like a weak constraint. Surely many ways to draw the maps satisfy it. Now imagine someone proves that the constraint is so rigid, it fixes the size of every country on every map uniquely, leaving no freedom whatsoever. That is what Gleason did to quantum probability. The gentle-sounding demand of consistency turns out to be a straitjacket with exactly one occupant. And here is the corollary that guts the hidden variable dream. Remember the dispersion-free state, the one that assigns a sharp 0 or 1 to every observable, the state a deterministic hidden theory would need. Gleason's theorem says that in dimension 3 or higher, no such state exists. None. You cannot consistently paint every direction with a definite yes or no. The moment you try, some complete measurement fails to sum correctly. So the space of theories that could hide a definite, pre-existing, context-free answer under the chance is not small. It is empty. What does it mean that determinism, at the level of all observables at once, is not merely unobserved, but mathematically impossible under this one condition? It means Einstein's dream cannot be had for free. If you want it back, you will have to break the condition, and breaking it costs. That condition has a name, and the name is the key to the whole second half of the story: non-contextuality. Non-contextuality is the assumption that the value of a measurement depends only on what you are measuring, not on which other compatible things you measure alongside it. It sounds almost too obvious to name. Of course, the photon's polarization is what it is, regardless of what else you check at the same time. That is the intuition of a stable, objective world. Gleason's theorem quietly used that intuition, and a decade later, 2 more mathematicians would show that quantum mechanics violates it outright. Hold the word. Non-contextuality. It is the hinge the whole door swings on. 10 years after Gleason, in 1967, Simon Kochen and Ernst Specker made the assault direct. They asked, forget probabilities for a moment. Can you at least assign definite values, 0 or 1, to a specific finite set of measurements, such that the assignment respects the obvious logical relationships between them and doesn't depend on context? They built an explicit configuration of 117 directions in 3-dimensional space and proved that no consistent assignment exists. You cannot color all 117 of them yes or no without contradiction. Try, and somewhere the rules force a direction to be both. Why does that matter so much? Because it means there is no context-free set of pre-existing answers waiting to be revealed. The kochen-specker theorem shows that the value a measurement yields cannot be thought of as simply read off a property the system already had, independent of the measurement's context. What you get can depend on what you measure it with. Picture a locksmith who finds that a key's exact shape depends on which other keys are on the ring beside it. Change the neighbors, and the teeth rearrange. That is contextuality, and it is not a metaphor for our confusion. It is a theorem about the mathematics. Over the decades, the proof was sharpened. Adán Cabello and colleagues cut the 117 directions down to 18 in 4 dimensions in 1996,
and later work reached 13. Fewer directions, same iron conclusion. Notice the pattern building because it is the spine of what physicists actually hit when they dug. Gleason. The Born rule is the unique, consistent probability rule. Kochen-specker. You cannot hide definite context-free values underneath it. Each result closes a door on the "it's just our ignorance" belief, but each closes it under an assumption. Gleason assumed non-contextuality. Kochen-specker assumed non-contextuality. And a hidden variable theorist could still say, fine, I will build a contextual theory where the answer does depend on the full measurement setup. That door is still open. Remember it. It is the door through which one survivor eventually walks. But there is another assumption to test, and testing it is what turned this from mathematics into one of the great experimental sagas of the 20th century. The assumption is locality, the idea that what happens here cannot instantly depend on a choice made far away. And the man who turned that assumption into something you could measure in a laboratory was John Bell. Here is how Bell enters, and it matters that he enters as a skeptic, not a believer. In the mid-1960s, John Bell, a working physicist at the European Particle Laboratory, Irish, precise, deeply uneasy with the orthodox hand-waving about measurement, went back to von Neumann's famous 1932 proof that hidden variables were impossible. For 3 decades, that proof had been cited to shut down the hidden variable program. Bell read it carefully and found the flaw. Von Neumann had assumed that a certain property of measured averages, that the average of a sum equals the sum of the averages, must hold for the hidden states too. For quantum states, it does hold. For the hypothetical hidden states, Bell showed, there was no reason at all to assume it, and every reason not to. Bell called von Neumann's supposedly general and plausible postulate what it was: absurd. The great impossibility proof rested on an assumption smuggled in without justification. What does it mean that a proof by von Neumann stood unchallenged for 30 years and was wrong? It is the humbling seed I asked you to keep. It means we must hold even our strongest results up to the light and ask exactly which assumptions they rest on, which is precisely the discipline that makes the surviving results trustworthy. Bell did not demolish von Neumann to reopen the door for easy hidden variables. He demolished it to clear the ground for a real test, one that would corner the hidden variable dream in the one place it might still hide. Because Bell then did something extraordinary. He asked, suppose hidden variables do exist, and suppose they are local, no faster than light influence. Choices here cannot instantly affect outcomes there. What would such a world be forced to obey? He derived an inequality, later sharpened by Clauser, Horn, Shimoni, and Holt, into the form used in every experiment since. Take 2 entangled particles, send them far apart, and measure each along one of 2 settings. Combine the correlations into a single quantity, S. Bell proved that any local hidden variable theory, any world where the answers are set in advance, and nothing travels faster than light, must obey S less than or equal to 2. Quantum mechanics predicts S can climb as high as 2 times the square root of 2, about 2.828. The 2 pictures make different numbers. Now you can go to the lab. Feel what just happened. A philosophical dispute about whether the universe hides its answers. 100 years of argument between Einstein and Bohr that looked hopelessly untestable became a number you could measure with detectors and a data table. Bell turned metaphysics into an inequality. That is one of the most beautiful moves in the history of physics, and I return to it often because it is the model for how you make the deepest questions honest. You find the number where the 2 stories disagree, and you go and read the number. So they read it. In 1972, at Berkeley, Stuart Friedman and John Clauser ran the first real Bell test, using pairs of photons cascading out of excited calcium atoms, detectors about 5 meters apart, roughly 200 hours of data. The result violated the local hidden variable bound by 6 standard deviations. Local hidden variables were losing, But there were loopholes, ways a stubborn local theory might still sneak through, if, say, the measurement settings were fixed too early and the particles could have known them in advance. So the experiments got harder and more ruthless. In 1982, at Orsay near Paris, Alain Aspect and his colleagues built an apparatus that switched the measurement settings while the photons were already in flight, too late for any signal traveling at light speed to coordinate them. They measured S equals 2.697, plus or minus 15 thousandths, in near-perfect agreement with the quantum prediction, and far above the local bound of 2. The locality loophole was closing. Picture two surveyors sent to opposite ends of a valley, each told to pick a direction to look only at the last possible instant, their choices sealed from each other by the speed of light itself. And still, their measurements come back correlated more tightly than any prearranged plan could produce. But nature is a patient adversary, and a few loopholes remained for another 3 decades. The detectors weren't perfectly efficient. The settings weren't perfectly random and separated at the same time. Could a clever local theory still exploit the gaps? In 2015, at Delft in the Netherlands, Bas Hensen and colleagues finally closed them all at once. They entangled electron spins held in 2 diamonds, in nitrogen vacancy centers, tiny defects in the crystal, separated by 1.3 kilometers, about 0.8 of a mile, across the university campus. The distance was the point. At that separation, the whole measurement finished faster than light could cross from one lab to the other, enforcing strict separation. They found S equals 2.42, with a probability of only about 4% that local hidden variables could have faked it by chance. Later runs tightened it further. That is the loophole-free result. Combined with the photon experiments of the same year, it did what Bell's inequality was built to do. It ruled out local hidden variables as an explanation of the world, to the satisfaction of essentially the entire physics community. The 2022 Nobel Prize went to Aspect, Clauser, and Zeilinger for this line of work. So walk the ledger with me. Local hidden variables, excluded by experiment. Non-contextual hidden variables, excluded by kochen-specker. And the Born rule itself, proven unique by Gleason. 3 doors, 3 closings. The belief that quantum chance is just hidden information is now cornered into a very small, very strange room. But before we corner it completely, there is one more test, and it is my favorite, because it goes after the Born rule from an angle nobody expected. Everything so far has tested the outcomes. This tests the arithmetic of interference itself. And to see it, we need the double slit, then a third slit that shouldn't matter but does. You know the double slit experiment. Light through 2 slits makes a striped interference pattern because the wave from each slit adds to or cancels the other. The Born rule, buried in that pattern, contains a precise arithmetic claim. It says interference happens between pairs of paths, slit A with slit B, and only pairs. There is no genuinely 3-way interference term. In the 1990s, the physicist Raphael Sorkin at the Perimeter Institute noticed you could test exactly this. Open 3 slits and measure the pattern. Then measure every combination, each pair of slits, each single slit alone. Combine them in a specific sum, the 3-slit pattern minus the 3 2-slit patterns plus the 3 single-slit patterns. Call the result the third-order interference term, I3. Quantum mechanics, through the Born rule, makes a flat prediction. That combination equals 0, exactly. Not small, 0. Interference comes in pairs and nothing higher. Sorkin realized that if the Born rule were even slightly wrong, if reality secretly ran on some deeper rule with a cube in it instead of a square, this term would come out non-zero, and you could catch it. Think of an accountant who claims that in any 3-way transaction, the books balance perfectly once you account for every pair of parties, with no irreducible 3-way term left over. You can audit that claim directly. Sorkin handed physics the audit. In 2010, a team led by Urbasi Sinha, then at the Institute for Quantum Computing in Waterloo, ran the audit with single photons through a 3-slit mask. a movable blocking mask to open each combination, and a fiber detector about 180 millimeters away. They measured the third-order term and found it consistent with 0 to extraordinary precision, bounded to less than 1% of the ordinary two-path interference. In their best configuration, the deviation was about 7 thousandths, plus or minus under 2 thousandths. Sinha's own comment captured why it mattered. With so much effort going into theories of quantum gravity that might one day generalize quantum mechanics, it is vital to test the postulates precisely first. What does it mean that when you audit the Born rule's arithmetic directly, at the level of a fraction of a percent, it holds? It means the amplitude squared structure is not an approximation of something deeper we've caught a glimpse of. As far as the sharpest experiments can see, it is exact. There was a coda that shows how carefully this is done. In 2018, a follow-up by Sinha's group using microwaves through slots measured a non-zero third-order term, up to around 6%. For a moment it looked like a crack, but the team traced it precisely to boundary effects in how electromagnetic waves bend around the physical edges of the slots. A real physical effect of the apparatus, fully explained, and not a violation of the Born rule at all. The honesty of chasing that down, rather than trumpeting a false anomaly, is exactly the discipline that makes the null result trustworthy.
Now for the one gap in Gleason's fortress, the crack I promised we would return to. Gleason's theorem holds only in dimension 3 and above. In the simplest quantum system, a single two-state system called a qubit, dimension exactly 2, the theorem fails. In 2 dimensions, exotic probability assignments beyond the Born rule are mathematically possible. Gleason's proof cannot rule them out, because it needs the extra room of a third dimension to force the contradiction. For decades, that was a genuine loophole. The uniqueness of the Born rule had an exception exactly where the simplest experiments live. That crack was sealed in 2003 by Paul Bush, and to understand how, you need one generalization of what a measurement is. Von Neumann's measurements were sharp projectors, clean, orthogonal, all or nothing. But real measurements can be fuzzier, and the general mathematical description of any measurement is a positive operator-valued measure, a POVM, a set of positive operators called effects that sum to the identity without needing to be orthogonal or sharp. In symbols, the effects are all non-negative and add up to 1. This is the true, general language of measurement in modern quantum information. Bush proved a Gleason-type theorem for POVMs, and crucially, it works in every dimension, including 2. By using the richer structure of generalized measurements, he closed the qubit exception. The Born rule is now the unique, consistent probability rule everywhere, with no dimension left uncovered. So step back and take in the full fortress, because this is where the presentation ends and the weighing begins. The Born rule, unique by Gleason and Bush in every dimension. No context-free hidden values, kochen-specker. No local hidden values, Bell, confirmed loophole-free by Henson. No higher-order interference, Sorkin's arithmetic, audited by Sinha to a fraction of a percent. And the whole structure sits under the most precisely tested theory in science. The physicists who went digging for the machinery beneath quantum chance kept hitting the same flaw. Every shovel strike found the Born rule and nothing softer beneath it. Now the real question, is that flaw the bottom? Or have we only proven that whatever lies below must be very strange? Earlier I said we would return to the surviving door. Now we do. Let me be scrupulously fair here, because this is where lesser accounts cheat. It is tempting to say the theorems prove randomness is fundamental. They do not, and saying so would be false. What they prove is narrower and sharper, that any theory restoring definite, predictable individual outcomes must pay a specific, named price. It must be contextual, abandoning the idea that measurements simply read off pre-existing context-free properties. Or it must abandon the independence of measurement settings, the assumption that the experimenter's choices are free of the system being measured. Those are the 2 doors Gleason and Bell left ajar.
Let us walk through each surviving theory and see exactly which price it pays, and whether the evidence prefers it. Start with the orthodox view. Call it Copenhagen, the working stance in most textbooks and, in the 2011 survey of foundations researchers, the leading single position at 42%, though notice that means a majority did not favour it. On this view, the Born rule is simply a postulate. Measurement is primitive, the rule needs no derivation, you compute amplitude squared and you match experiment. Does it fit the evidence? Perfectly, it was built to. Gleason even hands it a bonus. The postulate you're assuming is the only consistent one, so you are not being arbitrary. Where does it fall short? It leaves the measurement problem untouched and the origin of the probability unexplained. It says the ledger gets an unexplained entry every time you look, and refuses to ask where the entry comes from. It is not wrong. It is silent exactly where the mystery is loudest. As Sean Carroll said, perhaps we can do better. So can we derive the Born rule instead of postulating it? Several camps say yes, and this is the live frontier. Consider first the many worlds picture of Hugh Everett, who in 1957, the same year as Gleason, proposed that the wave function never collapses at all. There is no jump, no unexplained entry. When you measure the photon, the world simply branches. One branch where it went left, one where it went right, both real, both containing a version of you. The Schrödinger equation runs forever, deterministic, and the appearance of chance is the experience of not knowing which branch you are in. It is elegant, it throws away the troublesome collapse entirely. But it creates a brutal problem. If every outcome happens, what does probability even mean? If both branches are real, in what sense is one outcome more likely than another? And why those specific Born weights, the amplitude squared numbers, rather than just counting branches 50-50? David Deutsch in 1999 tried to answer with decision theory. He argued that a rational agent living in a branching world, forced to place bets on outcomes, is provably compelled, on pain of behaving irrationally, to weight those bets by amplitude squared. His stated goal was to derive a tends to from a does, to extract probability from a theory that only ever says what definitely happens. David Wallace later turned this into a rigorous formal proof from a set of rationality axioms. Does it work? Here the field genuinely divides, and honesty requires laying the division bare. Supporters say it is the first real derivation of the Born rule from something deeper, rational choice plus the structure of branching. Critics, a serious list including Fuchs, Schack, Kent, Hemo and Potowski, argue the proof smuggles in the very thing it claims to derive, hiding a non-contextuality-like assumption inside the rationality axioms. Or that the meaning of probability in a deterministic world where everything happens remains incoherent no matter how you bet. The mathematics is real. What it proves depends on premises reasonable people reject. The evidence cannot decide because many worlds predict exactly the same Born statistics as everything else. That is the refrain you will hear for every rival now. They all predict the same numbers. Consider next Wojciech Zurek's approach, built on decoherence and a symmetry he named Envariance, environment-assisted invariance. Decoherence is solid, established physics. When a quantum system interacts with its vast environment, the delicate interference between its branches leaks into that environment and becomes practically unobservable, which is why big things look classical. Zurek pushed further. He showed that when a system is entangled with its environment, certain symmetric states have a property. You can swap two of the system's outcomes and undo the swap entirely by acting only on the environment. When the amplitudes are equal, the global state is genuinely unchanged by the swap, so the two outcomes must have equal probability, by symmetry alone, not by assumption. Extend the argument and you get the full amplitude squared rule. Probability equals the wave function squared, derived from a symmetry of entanglement. Is that the bedrock beneath the Born rule then? It is beautiful, and it feels less circular than the decision-theoretic route because it leans on a physical symmetry rather than on axioms of rationality. But Schlosshauer and Fine identified assumptions folded into the argument, and a 2025 no-go result limits how far invariance extends once you allow more general dynamics. The critics are not saying Zurek is wrong. They are saying he has not closed every gap, which raises the question underneath all of these. When is a derivation really a derivation, and when has it just relocated the assumption? What does it mean that three separate camps have each derived the Born rule, and each derivation is accused of hiding the rule in its premises? That question has a hard edge, delivered by the pure mathematics itself. Schlosshauer and Fine noted that even Gleason's theorem, the strongest formal result, the one that proves uniqueness, gives, in their words, rather little physical insight into why quantum probabilities take the form they do. Think about what that admission means. We can prove the Born rule is the only consistent rule. We still cannot say why reality is the kind of place where that rule, rather than no rule, governs. The proof tells you there is exactly one key that fits the lock. It does not tell you why there is a lock. Now, the survivors that keep determinism alive by paying the named prices, and this is where fairness matters most, because it is easy to wave them away, and wrong to. First, Bohmian mechanics, the pilot wave theory of Louis de Broglie and David Bohm. Bohm's 1952 papers did what Einstein wanted. They restored definite particle positions at all times. In this picture, the particle always has a real location, and the wave function acts as a guiding wave, pushing the particle along according to a precise law, the guidance equation, which sets each particle's velocity from the gradient of the wave function's phase. The photon does go one specific way through the mirror. It always had a position. Nothing is undetermined at the level of the particle. So how does a fully deterministic theory reproduce the random-looking Born statistics? Through the quantum equilibrium hypothesis, the assumption that particle positions are distributed according to the wave function squared, the same amplitude squared, now describing our ignorance of the exact starting position rather than an irreducible chance. Durr, Goldstein, and Zhang He argued in 1992 that this is not an extra postulate, but follows by a typicality argument. For the overwhelming majority of possible initial configurations of the particles in the universe, any subsystem you examine will show Born statistics. The randomness on this view comes from not knowing the precise initial conditions, exactly the coin flip picture Einstein hoped for. So did Bohm win? Did he restore Einstein's world? Here is the honest accounting. Bohmian mechanics is mathematically viable, fully deterministic at the particle level, and reproduces every prediction of standard quantum mechanics. But it does not evade Gleason and kochen-specker. It complies with them by paying their price. It is explicitly contextual. The value a measurement yields genuinely depends on the whole experimental arrangement, not on a context-free property the particle carried alone. And it is explicitly non-local. The guiding wave links distant particles instantly, so a measurement here can immediately shape a trajectory there. That non-locality is exactly what Bell's inequality permits. Bell tests kill local hidden variables, and Bohmian mechanics was never local. It survives by being the strangest kind of deterministic theory, one where the hidden answer exists but is contextual, non-local, and, some argue, has its own randomness smuggled back in through the uncertainty in those initial conditions. Then there is the most radical survivor, Gerard 't Hooft's cellular automaton interpretation, published in 2016. 't Hooft, a Nobel laureate of formidable reputation, proposes that beneath quantum mechanics lies a fully deterministic classical process, like the cells of a vast computational grid, updating by fixed rules, evolving in a preferred ontological basis of genuinely real states. If such a substrate exists, every outcome is fixed in advance, and the chance is pure ignorance, all the way down. How does he escape Bell's theorem, which forbids exactly this for local theories? By abandoning the other assumption, the freedom of measurement settings. In 't Hooft's world, the experimenter's choice of what to measure is itself correlated, through the deterministic substrate, with the system being measured. This is superdeterminism. The settings were never free, so the Bell correlations arise without any faster-than-light influence. Does the evidence support it? This is where weighing on the science, not on taste, matters. Superdeterminism is not ruled out by any experiment. It cannot be, because it explains any correlation by prior coordination. But that is precisely its weakness. A theory that can explain any possible result by appealing to unmeasurable initial correlations makes no distinctive prediction and is widely regarded as effectively unfalsifiable. It pays the steepest price of all. It saves determinism by sacrificing the assumption that we can freely choose what to measure, the assumption on which all of experimental science rests. It survives on 't Hooft's stature and mathematical seriousness, not on evidence, and it stands alone. Zero support in that 2011 poll, and no experiment pointing toward it.
One more camp deserves its due because it dissolves the problem rather than solving it. Cubism, from Christopher Fuchs, Rudiger Schack, and David Mermin. On this reading, the wavefunction is not a piece of the world at all. It is an agent's personal catalogue of beliefs, and the Born rule is a rule of rational betting, close kin to the ordinary laws of probability an idealized gambler must obey to stay consistent. The collapse, on this view, is not a physical event. It is just you updating your beliefs when you learn a result. The accountant's mysterious entry is simply the accountant writing down what they now know. The measurement problem evaporates because there was never a physical collapse to explain. The cost. Cubism abandons the picture of an observer-independent reality that the wavefunction was supposed to describe, and critics argue it still does not derive the specific squared form of the Born rule from pure Bayesian reasoning alone. In the poll, information-based views like this drew about a quarter of respondents, a substantial, serious camp. And underneath all of them sits one more recent result that sharpens the whole picture. In 2019, Luis Massanes, Thomas Galli, and Markus Müller proved that the measurement postulates of quantum mechanics, the Born rule among them, are, as they put it, operationally redundant. Given the rest of the quantum framework, if you simply demand that the way you carve a system into parts cannot change the theory's predictions, the Born rule is the only possibility. Massanes said it cleanly: the Born rule is not just a good guess, it is the only logically consistent guess. And Adán Cabello, weighing the whole landscape, located the real mystery precisely. Born's probability postulate is where the puzzle really is. Not in the Schrödinger equation, not in entanglement, right here in the rule for turning amplitude into odds. So now weigh it all, honestly, on the evidence. What does the evidence actually support? Two things, firmly. First, the Born rule is the unique, consistent, non-contextual probability rule, proven by Gleason and extended to every dimension by Bush, reinforced by the Massanes-Galli-Müller reconstruction. There is no rival rule waiting to replace it. Second, individual measurement outcomes carry no accessible predetermining information in any local, non-contextual theory. Kochen-specker and the loophole-free Bell tests slam those doors shut, confirmed to 6 standard deviations in 1972 and loophole-free in 2015. On the mainstream understanding, and against every simple version of the hidden variable dream, the chance is bedrock. That is the well-founded core, and it is genuinely one of the deepest results in physics. Physicists dug beneath quantum chance expecting machinery and hit floor. And here is the honest edge, which I will not paper over. The theorems do not prove that reality is, at its deepest level, genuinely indeterministic. They prove that if a deterministic layer exists, it must be contextual or non-local, or must give up the freedom of measurement settings, and the surviving deterministic theories, Bohmian mechanics and 't Hooft's automaton, do exactly that. Those theories are strange, they pay heavy prices,
and one of them is arguably unfalsifiable. But they are not experimentally excluded, because every one of these pictures, orthodox, many worlds, invariance, Bohmian, superdeterministic, cubist, predicts precisely the same Born statistics for every experiment ever performed. On the numbers, they are identical. What separates them is not evidence. It is what price you are willing to pay, and no measurement to date can force the choice. What does it mean that our sharpest theorems can prove a rule is unique and still cannot tell us whether the chance beneath it is irreducible or hidden? I think it means we have found a real boundary, not a temporary ignorance, but the current honest edge of what measurement can decide. Science describes, with breathtaking precision, how the odds behave. It has proven those odds cannot be replaced by any simpler rule. Whether the deepest layer of the world is truly ruled by chance, or by a deterministic machinery contorted enough to hide from every test, is a question the equations, as they stand, cannot settle. That question sits just past the edge of the evidence, and the intellectually honest thing is to leave it there, not to close it with a comforting story in either direction. When I first worked through all of this, that is the part that stayed with me. Not the precision, staggering as it is. The precision, oddly, is the comfortable part. What stays is the shape of the ignorance, the way the theorems fence off exactly what we cannot know, and hand us, inside that fence, one rule and only one. We can predict the odds of a single photon's path to a fraction of a percent forever, and we can prove no better rule exists. And we cannot say, and may never be able to say, whether the specific click on the specific detector was written somewhere we cannot reach, or written nowhere at all. Return with me to that footnote for a moment, because it hides a lesson about how physics actually advances. When Max Born corrected the amplitude to its square in the proof stage of his 1926 paper, he was not being careless. He was doing something rarer and harder. He was letting the data reshape the theory in real time. The scattering experiments he was trying to explain would not sit still for a probability that ran linear in the amplitude. Only the square gave numbers that matched the counts on the detectors. So the square was not chosen for beauty, it was forced by measurement, and then it hardened, over the following decades, into the axiom textbooks now state without apology. Think of a bridge engineer who sketches a support beam by intuition, then watches the load test gauges climb, and quietly thickens the steel to match the strain the structure actually feels. Born thickened his rule to match the strain of the data, and the rule has carried every load placed on it since, and the loads have been enormous. Consider what the amplitude squared rule quietly governs in a working laboratory. When a semiconductor engineer models electrons tunneling through the thin oxide barrier of a transistor, a barrier just a few nanometers thick, a few dozen atoms across, the probability that any given electron appears on the far side is an amplitude squared calculation, the Born rule applied to a tunneling wave function. Billions of those calculations, embodied in silicon, run in the device reading these words. When a chemist computes the shape of a molecular orbital to predict how two compounds will bind, the density of the electron cloud she draws is the wave function squared, the Born rule again, now painting the very geometry of chemistry. The rule that its own discoverer footnoted is not an abstraction hovering over exotic experiments. It is the load-bearing wall of the material world. What does it mean that a rule no one can derive from anything deeper is simultaneously the most heavily used quantitative rule in applied physics? It means the mystery and the reliability are not in tension, they are the same fact seen from two sides. The rule works everywhere precisely because it is the unique rule that can work anywhere, which is exactly what Gleason proved. The uniqueness is why the tunneling calculation and the orbital calculation and the electron magnetic moment calculation all speak the same probabilistic language and never contradict one another. Take away the uniqueness and you would expect fractures, regimes where amplitude squared failed and some rival arithmetic took over. there are no such fractures. The absence of fractures is Gleason's theorem written in the behavior of every laboratory on Earth. Let me make the density operator form of the rule concrete, because it is where the Born rule reaches its full generality and where von Neumann's machinery earns its keep. Not every quantum system is in a pure, perfectly known state. Often you have a statistical mixture, a beam of atoms, half prepared one way and half another, or a system entangled with an environment you cannot track. Von Neumann's answer was the density operator, written ρ, a single mathematical object that packages both the quantum superposition inside a state and your classical ignorance about which state you have. And the Born rule, in this general form, reads, the probability of an outcome equals the trace of ρ times the effect operator for that outcome. The trace being the operation that sums the diagonal, extracting a single real number from the matrix. In plain terms, hand the density operator and the outcome to this formula, and it returns the odds, whether your system is pure, mixed, entangled, or embedded in a noisy world. Picture an auditor handed two very different kinds of uncertainty in the same ledger. Some entries genuinely undetermined until settled, others merely unknown to the auditor but fixed in fact, and given a single procedure that produces the correct expected total from both kinds at once, never needing to know which uncertainty is which. That is what the trace ρ times effect formula does. It does not care whether the fuzziness in your knowledge is the deep quantum kind or the ordinary ignorance kind. It processes both and returns a consistent probability. Gleason's theorem, extended by Paul Bush to this general operator language, proves that this procedure, too, is unique. There is no second auditor, no rival formula, that handles mixed and generalized measurements consistently. The generalization did not open a new door for alternatives, it closed the last ones. Now follow the effect operators one layer deeper into the POVM formalism, because this is where the modern understanding of measurement lives and where the qubit rescue actually happened. In the old von Neumann picture, a measurement was a set of sharp, mutually perpendicular projectors, clean yes or no questions at right angles to one another. But that picture is too rigid to describe real instruments, which are noisy, overlapping, and imperfect. The general description is the positive operator valued measure, a collection of effect operators, each one non-negative, together summing to the identity. The completeness condition, that the effects add up to 1, is just the statement that some outcome always occurs. The probabilities of all possible results must total 100%. What the POVM adds is that the effects need not be perpendicular. They can overlap. A single quantum system can be interrogated by a richer set of questions than the sharp projectors allow. Why does that richness rescue the Born rule in 2 dimensions? Here is the crux, and it is genuinely elegant. Gleason's original proof needed 3 dimensions because it relied on the rigid geometry of perpendicular directions to force its contradiction. A qubit, living in a flat 2-dimensional space, simply does not have enough perpendicular directions to trap an alternative rule. But POVMs are not confined to perpendicular directions. Even in 2 dimensions, the space of possible effect operators is rich and overlapping enough to reconstruct the very rigidity Gleason exploited in higher dimensions. Bush showed, in 2003, that once you demand consistency across all these overlapping measurements, the qubit is boxed in exactly as the higher dimensional systems were. Think of a surveyor who cannot triangulate a point using only 2 perpendicular sightlines, but who, granted the freedom to sight from many overlapping angles, pins the point precisely. Bush granted the extra sightlines, and the qubit's freedom vanished. So the fortress has no wall left unmanned. And that completeness is worth pausing on, because it changes the character of the claim. Before Bush, a determined hidden variable theorist could retreat to the qubit and say, "Your uniqueness proof does not reach here. In the simplest system of all, so perhaps the Born rule is only contingently true and something else governs the elementary case. After 2003, that retreat was cut off. The Born rule is now the unique, consistent probability assignment for every quantum system without exception. One electron spin, one photon polarization, or 1,000 entangled particles. What does it mean that the last hiding place for an alternative rule was the simplest system imaginable, and that it too was sealed? It means the search for a replacement rule is not merely difficult, it is provably over. The uniqueness is total. But uniqueness of the rule is not the same as understanding where its probabilities come from, and it is worth being scrupulous about that distinction, because it is the distinction the whole second half of the debate turns on. Gleason tells you that if you assign probabilities at all, under non-contextuality, you must assign them the Born way. He does not tell you why the world assigns probabilities rather than definite values in the first place. It is like proving that a language, if it is to be spoken consistently, must obey exactly one grammar, a powerful result, without explaining why there is speech at all rather than silence. The grammar is fixed. The existence of the utterance is a separate question. Schlosshauer and Fine were pointing at precisely this gap when they observed that Gleason's theorem, for all its mathematical elegance, gives rather little physical insight into the emergence of the probabilities themselves. That gap is exactly the territory the derivation programs try to cross, and it is worth walking each one a little further to see where the ground gives way. Return to the decoherence program, because decoherence is the part everyone accepts, and it is easy to overclaim what it delivers. When the photon in our mirror experiment interacts with the environment, stray air molecules, thermal photons, the detector itself, the crisp interference between went left and went right does not vanish, but it disperses into correlations with countless environmental particles, spread so widely that no feasible measurement could ever gather them back to reveal the interference. In practice, the two branches stop interfering. The system looks classical. This is real, measured physics. Experiments with larger and larger molecules, carbon-60 and beyond, have watched interference fade precisely as environmental coupling increases, exactly as decoherence predicts. Decoherence explains why we see definite outcomes rather than smeared superpositions. But does decoherence explain the probabilities of those outcomes? No, and this is the subtle point that trips up popular accounts. Decoherence tells you that the branches have separated and stopped talking to each other. It does not, by itself, tell you why the branch you find yourself in occurs with probability equal to its amplitude squared rather than some other weighting. That is the extra step Zurek's invariance was built to supply, and it is why invariance, not decoherence alone, is the load-bearing part of his derivation. The distinction matters because it marks exactly where the accepted physics ends and the contested derivation begins. Decoherence, established. The Born weights from decoherence alone, not established. Invariance is the attempted bridge across that precise gap, and the criticism of invariance is a criticism of the bridge, not of the solid ground on either side. Follow the invariance argument once more, slowly, because its structure reveals both its power and its exposed flank. Zurek considers a system entangled with an environment, written as a sum of terms, each term pairing a system outcome with a corresponding environment state. When the amplitudes of two such terms are exactly equal in magnitude, he shows you can perform a swap on the system that exchanges the two outcomes, and then perform a compensating swap purely on the environment that exactly undoes the global effect. The full state is left invariant, and here is the leverage. If a physical operation swaps two outcomes yet leaves the total state unchanged, then those two outcomes cannot differ in any physical property, including their probability. By pure symmetry, they must be equally likely. From equal amplitudes, equal probabilities, with no probabilistic assumption inserted by hand. Extend the reasoning to unequal amplitudes by breaking them into equal fine-grained pieces, and the full amplitude squared rule follows. Where does that flank lie exposed? In the phrase "cannot differ in any physical property," critics ask whether that step already assumes what a probability is and how it attaches to states. Whether, in insisting that a symmetry of the state must be a symmetry of the probabilities, Zurek has quietly imported a principle every bit as strong as non-contextuality. And the 2025 no-go result sharpens the worry from another direction. It shows that once you allow the dynamics to be non-unitary, to depart from the perfectly reversible evolution Zurek assumes, the invariant symmetry no longer pins the probabilities uniquely. The bridge holds under idealized conditions and strains under more general ones. This is not a refutation, it is the honest fine print. The derivation works if you grant its premises, and reasonable physicists disagree about whether the premises are free of the conclusion. The same shape of dispute haunts the decision-theoretic route, and it is worth voicing the objection a skeptic would raise, out loud, because it is the sharpest one. Deutsch and Wallace ask you to imagine a rational agent in a branching Everettian world, placing bets on which branch's outcome she will experience, and they prove that consistency of her betting forces amplitude-squared weights. The skeptic's objection is immediate. In a world where every outcome happens and a copy of the agent experiences each one, what does it even mean to bet on an outcome? Every bet is won by some copy and lost by another. The ordinary meaning of probability, the chance that this happens rather than that, seems to dissolve when both happen with certainty. Wallace's reply is that rationality can still be defined operationally, through the agent's preferences over branch-structured rewards, without needing a prior notion of chance. Whether that reply succeeds, or whether it smuggles the notion of chance back in through the structure of the preferences, is precisely the unresolved knot. The mathematics is not in doubt. The interpretation of the mathematics is the whole battlefield. What does it mean that three sophisticated derivations, decision theory, invariance, operational reconstruction, each reach the Born rule and each stand accused of assuming a cousin of the very thing they derive? I think it points to something structural rather than accidental. The Born rule may be so deeply woven into what we mean by consistent probability in a quantum world that any argument rich enough to reach it must already stand on ground shaped by it. That would not make the rule false or arbitrary, quite the opposite. It would make it something closer to a fixed point, a statement you cannot get underneath without, in some form, already using it. Gleason's uniqueness and this recurring circularity would then be two faces of one fact. The rule is unique because there is nowhere consistent to stand that is not already inside it. That reading gains force from the Massanes, Galli and Müller result of 2019, which is worth setting out precisely because it attacks the problem from the cleanest possible angle. They set aside interpretation entirely and asked a structural question. Given the mathematical framework of quantum states, what measurement rules are even possible? They imposed a single, almost innocuous requirement, that the predictions of the theory must not change depending on how you choose to mentally partition a large system into subsystems. If I describe a pair of particles as one four-dimensional system or as two two-dimensional systems, the physics I predict had better be the same, that is all. From that lone consistency demand, they proved the Born rule is the only measurement rule that survives. Massanes stated the upshot without hedging. The Born rule is not just a good guess, it is the only logically consistent guess. Sit with how that reframes the mystery. Before this result, one could imagine the Born rule as one option among many, selected by nature for reasons unknown. After it, the Born rule looks less like a choice and more like a theorem of consistency, the price of demanding that the universe not contradict itself when you slice it into parts. Picture an accountant who discovers that once you require the books of a corporation to balance, no matter how you draw the boundaries between its divisions being an arbitrary human choice, there is exactly one accounting convention that never produces a contradiction. The convention was not decreed, it was forced by the refusal to contradict. Adán Cabello, surveying this whole landscape of results, placed the mystery exactly where it belongs. Born's probability postulate is where the puzzle really is. Everything else in the framework, he was saying, is comparatively well understood. The one hard knot is the rule for turning amplitude into experience. Let me now hold the two surviving deterministic theories side by side, because comparing their prices directly is the clearest way to see what the evidence does and does not force. Bohmian mechanics and T. Hooft's cellular automaton both restore Einstein's dream of definite, predetermined outcomes. But they pay for it with different currencies, and examining which currency each spends tells you a great deal about the shape of the constraint. Bohm pays with contextuality and non-locality. His particles have definite positions, but the value a measurement reveals depends on the full apparatus, and the guiding wave links distant particles instantly. He does not violate any theorem. He satisfies Bell's inequality by being frankly non-local, and satisfies kochen-specker by being frankly contextual. He walks through the doors those theorems left open and pays the posted toll. Hooft pays with a different, arguably heavier currency, the freedom of measurement settings. In his world, the substrate is local and deterministic, cells updating by fixed rules. But the price of reconciling that with Bell's confirmed violations is superdeterminism, the assumption that the experimenter's choice of measurement was itself pre-correlated, through the deterministic history of the universe, with the state being measured. Consider what that demands. Every Bell experiment ever run, the settings chosen by human whim, by quantum random number generators, in the 2018 cosmic Bell tests, even by light from distant quasars billions of years old. All of it on the superdeterministic account, secretly coordinated with the particles being tested, so that the correlations only appear to violate locality. Picture a card game where you become convinced the deck is rigged, but the only way the rigging can work is if every shuffle you have ever made, including the ones you made to test for rigging, was itself determined in advance to cooperate with the con. At some point, the hypothesis explains too much to explain anything. Which of these prices does the evidence prefer? Here we must be exact and refuse both the temptation to dismiss and the temptation to endorse. No experiment excludes Bohmian mechanics. It reproduces every quantum prediction by construction. No experiment excludes superdeterminism either. For the same structural reason and more, it can absorb any correlation whatsoever into prior coordination. But cannot be excluded by experiment is not the same as supported by evidence. A theory earns evidential support by making distinctive, risky predictions that then come true. Bohmian mechanics makes no prediction that differs from standard quantum mechanics, so it earns no distinctive support. It survives as a viable reformulation, not as a discovery. Superdeterminism makes no risky prediction even in principle, which is why it is widely judged effectively unfalsifiable, and why it draws no experimental support at all. The 2011 poll of Foundations researchers recorded 0% favoring the pilot wave picture, and no measurable constituency for superdeterminism, not because the mathematics is wrong, but because the community weights unfalsifiable machinery lightly. What does it mean that a theory can be unkillable and unsupported at the same time? It means falsifiability and truth are not the same axis, and honesty requires reporting both coordinates. There is a further, quieter observation that cuts against reading Bohm as a full restoration of determinism, and it deserves airing because it is easy to miss. The randomness that Bohmian mechanics appears to banish at the level of particle trajectories re-enters through the back door of the quantum equilibrium hypothesis. Recall that Born statistics emerge in Bohm's theory only because particle positions are assumed distributed as the wave function squared. Where does that distribution come from? From the initial conditions of the universe. And the typicality argument of Durr, Goldstein, and Zangi secures Born statistics only for the overwhelming majority of possible initial configurations. which means the randomness has not been eliminated. It has been relocated to the setting of those initial conditions. Some analysts put the point starkly. Bohmian mechanics is not truly deterministic in the sense Einstein wanted, because the unpredictability of any individual outcome now rests on our irreducible ignorance of an initial configuration we can never access. The chance was not abolished. It was moved to the beginning and hidden there.
That relocation is deeply telling. Trace the pattern across every attempt to remove quantum chance. Copenhagen posts it openly as a postulate. Many Worlds tries to dissolve it into branch counting and finds it reappears as the puzzle of what probability means when everything happens. Invariance tries to derive it from symmetry and finds critics who say the symmetry already contains it. Bohm tries to bury it in trajectories and finds it resurfacing in the initial conditions. 't Hooft tries to eliminate it in a deterministic substrate and finds he must sacrifice the freedom of experiment to do so. In every case, the chance is not so much removed as displaced, pushed to a different location in the theory, where it sits, compressed but undiminished. Picture a person pressing down on one corner of a stretched rubber sheet. The bulge does not vanish, it migrates to another corner. Quantum probability behaves like that bulge. Every theory that presses it flat somewhere raises it somewhere else. What does it mean that the chance can be relocated, but never in any theory cleanly erased? This is, I think, the deepest empirical lesson of the whole century-long effort, and it is a lesson about the structure of possible theories rather than about any single one. It says that the amplitude-squared probability is not a defect to be engineered away, but a feature woven so tightly into the quantum framework that removing it from one place forces it into another. That is not a proof that the deepest layer of reality is irreducibly random. I have been careful throughout not to claim that, because it is not something the theorems establish. It is the observation that no one has found a formulation where the chance simply is not there, and that the theorems explain why the search has been so hard. The rule is unique. The hidden values are contextual or non-local or unfree, and the derivations keep circling back to the thing they set out to derive. Let me anchor all of this back in the laboratory one final time, because the abstraction should never float free of the measured world, and the precision tests deserve their full weight. The reason any of this matters, the reason the uniqueness of the Born rule is not a mere curiosity of pure mathematics, is that the rule is under constant, ferocious experimental pressure, and it never cracks. Return to the electron's magnetic moment, measured by the Gabriel's group to about 1 part in a trillion, 13 decimal places of agreement between theory and experiment. Every step of that theoretical prediction, from the bare electron to the swarm of virtual particles that dress it, is computed by squaring amplitudes and summing them, the Born rule applied billions of times over in the perturbation series of quantum electrodynamics. If the amplitude-squared rule were even slightly wrong, if some third-order interference term crept in at the level Sorkin imagined, that agreement would fracture at some decimal place. It does not fracture. The most precise number humans have ever extracted from nature is a monument to the exactness of the Born rule. And the direct audits, Sorkin's and Sinha's, press on the rule from the complementary side. The precision tests confirm that amplitude squared gives the right answers. The interference audits confirm that the amplitude squared structure itself, pairs only, no genuine three-way term, is exactly right. Sinha's 2010 bound placed the third-order term below 1% of the ordinary two-path interference, with her best configuration measuring a deviation of about 7 thousandths. Later work with 5 paths and the microwave follow-ups that carefully traced an apparent anomaly to boundary effects rather than to any breakdown of the rule, all converge on the same verdict. From 2 directions at once, the accuracy of the predictions and the structure of the interference, the Born rule is confirmed to be not approximately right,
but, within the reach of every experiment yet performed, exact. What does it mean that a rule this heavily audited from this many independent angles has never once been caught bending? It means that when physicists say they hit bedrock, they are not speaking loosely. They mean the shovel keeps striking the same unyielding floor, and the floor keeps ringing true. I return often to one particular figure in this story, and it is not a number but a person, John Bell, patiently rereading a proof everyone else had trusted for 30 years and finding the flaw. Bell is the conscience of this entire subject. He is the one who refused to let von Neumann's authority stand in for an argument, who insisted that every impossibility claim be examined for the assumption it hid, and who then, having cleared away the false impossibility, built the true one, the inequality that turned a metaphysical quarrel into a measurable number. The discipline Bell embodied is exactly the discipline that makes the modern verdict trustworthy. We can say the Born rule is bedrock and mean it precisely because people like Bell spent their careers trying to prove it was not, and failing honestly. A result that has survived its most determined opponents is worth more than one that was never seriously attacked. There is one more thread to draw tight before the resolution, and it concerns the strange gift hidden inside all this constraint. The theorems do not only close doors, they also draw, with unusual sharpness, the exact boundary between what we can know and what we cannot. Under the Born rule, we can predict the statistical distribution of outcomes with perfect, unlimited accuracy, run the experiment enough times and the frequencies converge on the amplitude-squared prediction to any precision you demand. And we cannot, by any theorem-permitted means in a local, non-contextual world, predict the individual result. The knowable and the unknowable are separated by a line the mathematics draws precisely. The ensemble is fully open to us, the single instance is closed. That is not the fuzzy ignorance of a coin flip, where finer measurement would in principle reveal the answer. It is a structural partition, drawn by the theorems themselves, between the domain we command completely and the domain we cannot enter at all. What does it mean that the same rule which grants us perfect mastery of the odds forbids us all access to the individual case? It means the limit is not a temporary failure of instruments, but a feature of the description. The very rule that opens the statistical world locks the single event. Consider how unusual that pairing is against the rest of physics. In classical physics, more precise knowledge always buys more precise prediction. The two rise together without a ceiling, and the only barrier is practical. A meteorologist with better sensors forecasts further. An astronomer with a finer clock predicts an eclipse to the second. The Born rule breaks that monotonic bargain. It hands you the statistical distribution outright, gift-wrapped and exact, and then draws a hard line you cannot cross toward the individual outcome, no matter how much you refine your knowledge. Picture an insurance actuary who can state with flawless precision that a certain fraction of 1,000,000 policies will be claimed this year, and who is provably barred, by the structure of the world rather than by any lack of data, from ever knowing which policies. The classical actuary lacks only information. The quantum actuary faces a theorem. That difference is the whole subject compressed into a single image. This is the part that I find genuinely alters how I think about knowledge itself. We tend to assume that the unknown is simply the not yet known, that every closed door yields to a better key. The Born rule, buttressed by Gleason and Kochen-specker and Bell, and the loophole-free experiments, presents something different. A door for which no key exists in any local, non-contextual theory, and for which the surviving keys, Bohms, 't Hooft's, open only onto rooms furnished with contextuality, non-locality, or the surrender of experimental freedom. The unknown here is not a gap in our maps. It is drawn on the map as a boundary, with the theorems as the surveyor's marks. And the boundary is honest in a way that comfortable mysteries are not. It tells you exactly how far you can go, and exactly what it would cost to go further. Let me place that boundary against the sweep of the whole 100-year effort, because the timeline itself tells a story of steadily tightening constraint. In 1926, Born wrote the rule as a footnote to a scattering calculation. In 1932, von Neumann built the formal scaffolding and offered a proof that hidden variables were impossible, a proof later found to rest on an unjustified assumption. In 1952, Bohm showed that determinism was in fact possible, at the price of non-locality and contextuality. In 1957, Gleason proved the rule unique above 2 dimensions, and Everett proposed doing away with collapse entirely. In 1964 and 1966, Bell dismantled the false impossibility and erected the true inequality. In 1967, Kochen-specker closed the door on context-free hidden values. From 1972 through 2015, the experimentalists, Friedman and Clauser, Aspect, Henson and the Delft team, hunted down every loophole until local hidden variables lay excluded beyond reasonable doubt. In 1994, Sorkin found a way to audit the rule's arithmetic directly, and in 2010, Sinha ran the audit. In 2003, Bush sealed the qubit exception. In 2019, Massanes, Galli and Muller showed the rule was the only consistent measurement postulate at all. Each date is a door closing. Read end to end, the timeline is the sound of a search narrowing toward a single, unavoidable flaw. What does it mean that a century of the sharpest minds in physics, attacking the problem from mathematics, from experiment, from philosophy, and from information theory, converged on the same rule Born footnoted in 1926? It could mean 2 things, and the honest position holds both without collapsing them. It could mean the Born rule is the genuine bedrock of quantum probability, irreducible, the place where explanation bottoms out, the reading the mainstream evidence most strongly supports. Or it could mean the rule is a fixed point so central that every deeper theory must reproduce it, in which case there might yet be a substrate beneath, deterministic but contorted, forever making the same predictions and forever undecidable by experiment. The theorems are consistent with both. What the theorems exclude is the comfortable middle the belief started from, the simple, local, non-contextual, hidden layer that would let us keep our classical intuitions intact. That middle ground is gone. It was proven empty and confirmed empty in the laboratory. I want to be precise about the emotional register of that conclusion because it is easy to hear it as either triumph or defeat, and it is neither. It is not a triumph of chance wins because the theorems do not prove chance is metaphysically ultimate. The deterministic survivors remain, wearing their heavy prices. It is not a defeat of "we failed to explain," because the uniqueness proofs are among the most complete explanations physics has ever produced. They tell us not merely what the rule is, but that no other rule is possible under the stated conditions. It is something rarer and more mature, a precise cartography of a limit. We know the shape of what we know. We know the shape of what we do not, and we know exactly which assumptions separate the two. That is not the end of inquiry. It is inquiry arriving at a place clear enough to see its own edges. Let me bring this exploration to a close. We began with light crossing a pane of glass, part of every beam reflected and part passed through, and a single photon that lands on one detector for a reason you could never recover. We watched Max Born wedge the probability rule into a footnote in 1926, correcting the amplitude to its square because the scattering data demanded it, and we saw that footnoted rule grow into the load-bearing wall of the material world, governing the transistor, the molecular orbital, and the electron's magnetic moment, matched to theory to about 1 part in a trillion, the most precise contact humans have ever made with nature. We followed Andrew Gleason, who in 1957 proved the Born rule the only consistent non-contextual probability rule in 3 dimensions or more, and Paul Bush, who in 2003 sealed the last qubit-sized gap so that no system anywhere escapes it. We watched Simon Kochen and Ernst Specker prove there are no context-free hidden answers waiting to be read, and John Bell, rereading von Neumann, finding the hidden flaw and forging the inequality, turn a century-old quarrel between Einstein and Bohr into a number the laboratory could measure. And the laboratory measured it. Friedman and Clauser at 6 standard deviations, Aspect with his settings switched in mid-flight, the Delft experiment loophole-free across 1.3 kilometers of campus. We audited the rule's own arithmetic through Raphael Sorkin's third-order interference and Abbasi Sinha's 3-slit measurement, and found it exact to a fraction of a percent. Then we weighed the survivors, fairly and on the evidence, orthodox silence, Everett's branching worlds, Zurek's Envariance, Deutsch and Wallace's rational betting, Bohm's guided particles, Tooft's deterministic substrate, Fuchs's degrees of belief, and found that every one of them reproduces the same Born statistics, so that no experiment ever performed can choose between them. We watched the chance refuse to be erased. Pressed flat in one theory, it bulges up in another, relocated to initial conditions, or to the meaning of probability, or to the sacrifice of experimental freedom, compressed but never gone. Here is where the evidence leaves us. The Born rule is unique, that is proven, by Gleason and Bush, in every dimension, and reinforced by the reconstruction of Massanes, Galli, and Muller. No simple, local, non-contextual hidden layer can restore predictable individual outcomes. That is proven by kochen-specker and by Bell, and confirmed in the laboratory beyond reasonable doubt. Against every simple form of the belief we started with, that quantum chance is merely our ignorance, waiting for a smarter theory to dissolve it, the digging has struck flaw, and the flaw has rung true under every strike. That much is well-founded, and it is one of the deepest results physics has ever reached. And here is the edge that stays open, which no amount of precision closes. Whether the deepest layer of reality is genuinely governed by chance, or whether some contorted deterministic machinery, contextual, non-local, or robbed of free measurement, lies beneath it making identical predictions forever, is not something the equations, as they stand, can settle. The rival pictures agree on every number. What separates them is the price each is willing to pay, not any measurement we can take. That question sits just past the boundary the theorems draw, and the honest thing is to leave it there, resolved neither toward a hidden order nor toward blind necessity, but named plainly as the current edge of what measurement can decide. If you have found value in following this argument to its flaw, consider subscribing. It helps these deep explorations reach more curious minds who would rather sit with a precise question than a comfortable answer. We went looking for the machinery beneath the chance, and found instead a single rule, footnoted a century ago, proven to be the only one there is, a flaw with no hidden room below it, only the exact, honest distance between the odds we can command and the outcome we were never meant to hold.